All right, so I just emailed out your midterm exams. Your grades are posted, that type of thing. We did overall much better. Not sure how much of that is you getting used to the way I exam test, or I graded easier, or it was just an easier test. I don't know, but class average was 91.4 with standard deviation of 6. So overall, pretty good. Um, we'll You're, as I said in the announcement email I sent out yesterday, I tried to weight it. That reflects the different weightings of your homework and exam and midterms and that type of thing, as it would in a final grade. I didn't work too hard at that, and I didn't make any adjustments. As I've said, there's a couple of things going on. If you blew your first exam and then hit the final exam out of the park, your grade's going to reflect what you know at the end of the course, right? So there will be some adjustments made. So don't panic if your grade is still kind of being pulled down by that first exam. Also, I will give some opportunity for some extra credit. Probably post after class sometime a couple of problems that actually someone asked if they could do some extra credit over spring break. So yeah, I'm going to do that. Basically, it's I'm going to create or pick some problem out of the book or some other book that talks about partial response signaling, which is another way of handling the problem of InterSymbol interference, which we'll talk about today. But I really don't have time to get into that as a particular topic. And then there's, I'll think of some other things also that you can do. If you're doing fine in the course, don't worry about it. Don't do the extra credit. I'm not going to make it due right after spring break in case, you have other plans and you think, oh, it's not fair, type thing. So I'll give everyone some time on this extra credit, but if you want to use spring break as a time to get caught up, that's what I'm going to do. And we'll find some time to relax, but a lot of it's going to be catching up. So all right, enough of that. So hopefully that'll make sense for everyone. I did kind of fill out a class schedule. Normally I do this at the beginning of the semester, as I prepare a class and that type of thing. But as we know, I kind of got tossed into this at literally well, maybe not literally the last minute, but the last day before the semester started. So just getting to the point now where I think we can kind of have a clear sight on the rest of the semester. So hopefully we can get through all this introductory stuff and talk about band limited channels today, error control coding and block codes after spring break, and trellis codes, and maybe the Viterbi decoder. That's a ton of information, and you can do a whole course on this, multiple courses on this, but I'll try to figure out how to get you some exposure that's meaningful, not just a total survey of things, but actually something meaningful, but compacted into two sessions. The vocoder, that's kind of it's, maybe I could call it source encoding. It's the idea of taking your input signal and compressing it for transmission. If we're running long on these error control codings, I think we'll kind of drop that and just let these bleed over. It does mention in the course description a little bit about source encoding. feel like that's not as important of a topic, but it is interesting. So we'll do something about that. I would love to do a lab and a couple of labs. So I'm trying to figure out the logistics of that. And I'd like to do one with MATLAB and another one with GNU Radio. I think this MATLAB will be a little bit easier if we can get access to the lab that holds those. I'm looking into that, and also, and we'll enter April with receiver noise analysis, look at spread spectrum, fading channels, coherence, bandwidth. Oh, this is a PDF. I can't edit that. Sorry, that should be a comma. And some of the empirical models associated with channels. Look at diversity. When we say diversity in communication systems, that means looking at multiple different ways of getting your information across the channel. And it's particularly important in complex fading channels where you might have direct path, you might have multiple different reflected paths. And so if you use multiple antennas, MIMO stands for multiple input, multiple output. It means basically multiple antennas. Can you see that on that cell tower back there? No, that's not really a cell tower. But if you look at cell towers, they usually have like 2 to 4 antennas facing out into a sector. And so that's actually adding diversity. And sometimes you just pick the best one out of all of them, or sometimes you're able to combine multiple ones. So even if they're all kind of lousy, if you combine them in an intelligent way, you get good results out of them. And then we'll look at orthogonal frequency division multiplexing. That's been kind of the go-to waveform for later versions of Wi-Fi, WiMAX, LTE, and 5G type radio communication systems, and particularly to try to deal with these fading channels type of problem. GNU Radio is a kind of open source software defined radio. So you can actually run that on your computer. And if you can have just enough electronics to sample the waveform and get it down into a frequency range that you can work with, then you can do all this decoding and all these things that we've talked about and much more in software on a computer. So hopefully we can pull that off. And then we'll wrap up the course looking a little bit about standards. Communications is very much a standards-driven process. Look at research direction. I might talk a little bit about SATCOM because I've done satellite communications because I've done a lot of work in that area. But yeah, we're going to run out of time. And then we'll do a semester review. I think if I've looked it up correctly and I've done my time zone conversion correctly, we'll have a final exam on Tuesday the 9th. And I am currently planning on visiting my daughters in New York around this time frame. So you might see me in class. No promises. Or maybe you consider that a threat instead of a promise. But all right, so let's look at the exam really quickly. I think a lot of these things you guys are on top of now. So good job. Shannon's capacity theorem, now we're actually using it to calculate. And just again, remembering that Shannon's capacity theorem gives you an upper limit of things, right? So some of y'all didn't carry through the units properly and that type of thing. I forgave you on that and all, but we'll talk about that momentarily. Using Shannon's concept of entropy. So I think we're starting to get this. Some people still are missing this. I almost put the equation down. I know I had it in a preview. I didn't put it on your your sheet, but really you're expected to identify the concept that a low probability event is actually carrying a lot more information because it's talking about surprise, something you didn't know beforehand. And so that has high entropy. So a low one has a low probability of an event, has a high probability. So FSK, again, that was something we had a hard time on the first exam, and I think most people are getting that. Again, a lot of times we're specifying things in terms of rate, but also other times we specify it in terms of period. So you need to be able to identify what is being talked about and adapt. The grade code, mostly we're working on this. You kind of had to come up with a 3-digit code. We did that in the homework, and we talked about a little handy dandy algorithmic approach to it. Some of y'all, most of y'all did fine on that. A few, I guess, forgot the algorithmic approach, but most people are kind of getting that concept. If you have 8 symbols, your M is equal to 8. K is going to be the size of your gray code, the number of digits in your gray code, and that's log base 2 of M, or log base 2 of 8. Need to get comfortable whether you're working in digital systems like using your Verilog or VHDL and FPGA, or embedded systems, or whatever. You do need to be comfortable with powers of 2 and that type of thing. That's our life in the digital age. So here's a gray code, and this one's easy compared to your homework assignment. You can just assign them in any order, starting where, go either direction, just be consistent. And like if you start up here, just make sure that as you end, that this transition also is only changing 1 bit. The decision areas now are still kind of splitting these constellation points and stuff. So try to make sure you really understand that concept, right? So this is the ideal symbol point right here. And where do you think, would be the region boundaries that you would use when trying to assign any, corrupted received signal to a particular point, right? So kind of apply a little bit of common sense there if you forget any particular rules or whatever. All right, this one, I kind of hinted on this on a preview when I was writing this one out. I was a little bit concerned because we use this formula in class, one of the lectures briefly, and it's on your formula sheet up here. A few people didn't quite identify that, that's the formula you need to use. I tried to kind of make it obvious. Actually, I think on the actual test, I changed these to P's, but so this is more of a specific case for binary antipodal signaling where you do not have equal probability. So you're creating a threshold here, right? So this formula is showing a threshold. Now, what I was trying to do, so I kind of modified this on that actual exam, so I gave you a chance to kind of explain what it meant, so you could get some points if you didn't get the formula exactly correct. But the idea here is you're creating a threshold that then defines the decision area, because symbol 1 is a higher probability than symbol 2 to be sent, then we make symbol 1 decision area associated with this symbol 1 larger to kind of account for the fact that, hey, we're most likely to get an S1 anyway. So let's open that area up to reflect that increased probability. If this was equal probable, because it's binary antipodal, right? So it's A and minus A up here, right? So it's lining along the x-axis and or the real axis, and your threshold in the equal probable case is 0. Anything greater than 0 or positive is going to get assigned to S1, and anything less than 0 or negative is going to get assigned to S2. When you consider the non-equal probable case, you'll see that your threshold is minus 6.4 micro volts or amplitude or whatever, and so it's a little bit less than 0. So that is widening up that D1 decision area. Of course, the areas are infinite because they go off to positive infinity on one side and negative infinity on the other side. But it is kind of in a limit. It's a little bit larger. All right. So hopefully you understand that solid now. So this one was like your homework assignment. So if you were working on a homework, I think that you did pretty well on this one. The idea here is that you're given the error probability that you're trying to achieve. Actually, it should be a 2 times right there, I think. So you look up the argument in the Q table that produces this error, right? So I tried to give you something that was easy to look up, and so then that argument in the Q gives you this error probability, and so you look at this argument now and assign that, and the rest is algebra. But again, keep track of rate versus period, and make sure you handle your math correctly. Some people actually observe that we're given the rates, and the formula has T, and they accounted for that, but then still just punched it in wrong. Okay, whatever. The noise here, one of the things you got to look out for is noise is usually specified as n naught over 2, so you need to carry that 2 along, and then just solve it. So then finally this one, this is kind of easy to get wrong. In fact, yeah.
We have a question.
Sure.
So does the amplitude have a unit, or it's just a ratio?
Well, the amplitude would likely be in volts, maybe millivolts, maybe something like that. But generally, you are looking at a voltage in a real signal. When we're dealing with math here, until we try to convert it to energy with joules or something like that, it's customary in digital communications to kind of ignore that actual scale of things, right? And that caused me trouble when I was first studying this, because I had already been working with RF electronics, and I was used to volts and watts and that type of thing. And that it actually doesn't matter what your actual voltage is. You can amplify it, you can attenuate it before you actually do the detection. What's really important is the signal to noise ratio. How much energy do you have in your signal? How much noise do you have? How much energy is there? So as long as you're consistent, it's fine. So when you're dealing at this level of digital communications, it's common not to even attribute a unit, much less a real value to it. That's why we've got A here. So yeah, we're technically calculating a numerical value for that. So I think the unit would be volts there, but it is an amplitude, and it's important to keep track of amplitude versus power or energy, because those are square root type of relationships. All right, so good question. For the correlation receiver, figure 1, and the match filter in figure 2, yeah, what's this? So again, this is one of those questions where if you mark the wrong one, then you would lose all the points. So I give you a chance to explain it. And so if your explanation was along the right direction, some people, and in fact, even when I originally kind of wrote out my solution, usually I write the test one day and then I work through it and create solutions another day. So I'm just trying to do it fresh and trying to assess how difficult the test is and that type of thing. And so even when I was doing it, I initially circled A. It's easy to get a little bit careless, but yeah, B is the essential concept, is that it's identical at this sampling instance, but different in between. So in fact, some people got the explanation correct in great detail and circled the wrong one, right? So all right, let's go back here. So question 5 is the type of question that I'll throw in every now and then to kind of test your understanding. Yes, it's a little bit of a plug and chug, find the right formula and just crank it out. But I do, toss in some things that I think are going to stretch you a little bit. When you see that, I tend to grade that very, very graciously. So everyone got some points for it, as long as you try to put something down for this and stuff. So don't freak out on those types of things. So all right, yeah, let's move on, and I'll post those solutions. I'll get them cleaned up. I saw some little typos in my solutions as I went through there. But all right, so we've done the exam review. As I've been looking at these things, I've kind of observed some things in some of your notes and that type of thing you put down on some of these exam questions. And I spent most of my career, even though I did teach professionally for a few years in Manhattan College, I spent most of my career in private industry, mostly in startups, and mostly in communication systems, actually, but more recently in AI. So I've interviewed a lot of people, I've hired a lot of people, developed them as teams and that type of thing. So got a little bit of an idea on what I think is essential for an entry-level engineer. You guys are within a few months. Maybe some of y'all have already got job offers. Maybe some are just ramping up your interview process. But yeah, so these are just something I scratched out. I don't know. I'll go through all of these for the sake of time. Let's see. Speaking of time, what time is it? Okay, we're doing okay. All right. How to determine units of an answer, right? So the question came up earlier: is what's the units of that amplitude? More, I think. Critical or whatever is like, Shannon's capacity theorem should give you a bits per second. If you look at that bandwidth out front there, everything else is a ratio in that logarithm. So you should have, a hertz or a bits per second type of unit. As you go through these things, you should be able to work with that and kind of rationalize your units through an equation. All right, and you got to know your metric prefixes. Maybe you don't know what an attogram is. I think it's 10 to the minus 18th, if I remember correctly, or femto even. But you ought to, as electrical engineers, you ought to understand pico, because capacitors are dimensioned in picofarads a lot of times. So all the way up to mega, giga. So you need to be able to recognize those, whether it's an abbreviation prefix or just a mega prefix. All right. and identify that the period is reciprocal of rate, and that type of thing. Rate's essentially equivalent to a frequency type of thing. So, know that the output of a linear system, let's say a filter or an amplifier or something like that, but or a control system, whatever. But the output of a linear system is the input signal convolved with the system's impulse response, right? And convolution is done by flipping one factor and sliding across the other while summing the area, integrating, right? The integration is the sum, while summing the area under the intersected region, right? And let's see. In the frequency domain, we can multiply the input frequency response with the frequency response of the system to produce the output frequency response. So, RF engineers tend to hate convolution. So we transfer everything into the frequency domain so we can multiply instead of having to do all that flipping and sliding and integrating and that type of thing. So the frequency response of a system is a Fourier transform of its impulse response. A steep slope in a time domain signal is reflected by high frequencies. Okay. A square wave signal is very steep on its edges, right? And so it requires an infinite number of odd harmonics. That's usually one of the first things you look at in your Fourier series expansion type lessons. And so it's an easy interview question to ask, right? So convolution of two rectangle functions or squares produces a triangle. The Fourier transform of a rect is the sinc function, the sine x over x. If you go try to get a job in signal processing or filter at a filter company, so I spent my first 13 years in my career as a filter engineer. That's something you do daily and should be intuitive. We haven't talked about in this class, but I recall from previous classes that I've taught, sometimes people don't, haven't quite mastered this. C, in this case, speed of light, but could just be the phase velocity of a electromagnetic wave is equal to the frequency times the wavelength, and be able to solve one way or another. Logarithms to linear units, working with those, common base, and dealing with exponents, a dot product producing the projections onto of a vector onto its basis functions or coordinate axis. All right, so you go through class, and we all do this, right? So you go through a whole bunch of classes over several years, and you're just trying desperately to get a good grade in each class, and then you move on to the next one, right? So but now's a good time to kind of sit back and reflect, right? And try to take all the knowledge you've learned in all these courses and kind of start making sense of it. That's why, maybe some of the stuff I just talked about is obvious, trivial, and all, and it is, but sometimes we just are scrambling so fast in our academic careers that we sometimes just need to stop for a moment and make sense of it all. So that's all that all those previous slides are. So now things that impress me in an interview, and whether you're going on to grad school or going right into your career, these are things that you could have these insights, but maybe you need to stop and really think about it, right? So understanding that with the Fourier transform process, you completely trade off resolution in a time domain for resolution in the frequency domain. In other words, if you're in a time domain, you really have no resolution or information about the frequency. Sure, you can see by the way the thing squiggle that maybe there's some high frequency content or something like that, but it's not there mathematically, right? So if you're in the frequency domain, you don't really have any idea on how things are changing, right? You kind of assume that they're just kind of static, right? If there's let's say a cosine signal in your and you do a Fourier transform of that, you're expecting to see this, kind of set of impulses, right? And positive and negative frequency. But that's only if that frequency or that signal is not changing while you're doing it. If you're changing, then it has a time dependency. It's no longer time invariant. And so that's you're losing all of that resolution. So there are techniques, wavelets are one of them, to trade off that resolution a little bit more friendly. But that's kind of a nice, sophisticated thing to understand. This one, I debated about whether that's impressive or not. I think it is. But you should definitely understand this, is that things that are bounded in the time domain, right? So they have like a square wave has, a bound to it, right? A pulse, a single rectangle function, and it's zero everywhere else, right? So it's bounded in the time domain. It's going to have an infinite frequency response, and vice versa. If you're bounded in the frequency domain, if you try to build a perfect filter, let's say, that's a rectangle in the frequency domain and only pass these frequencies and kill everything else, then you're going to need infinite amount of time in your signal to implement that. So understanding the assumptions, this is a top thing that I usually harp on and poke at. We often make these assumptions. You make very tight assumptions in your sophomore classes to be able to make the math easy enough, and maybe by the time you're a senior, we've relaxed some of those assumptions, and you relax even more as you go into more advanced studies. But things like that, they're linear. Well, a lot of systems are nonlinear, so you need to understand the implications of assuming that everything's linear. Time invariant, we just talked about that a little bit briefly. If you work in microwave systems, you're going to deal with this idea that, hey, is that resistor or capacitor really a lumped element, or the inductor? Is all the effect of that resistance in an infinitesimal point on that circuit, or is it really distributed? When the size of your component is significant with respect to the wavelength of the signal in it, you can no longer assume that it's a lumped element. You need to understand that signal is actually changing its phase as it rolls through that component. So microwave systems, we often have to drop that lumped element and consider distributed elements. Infinitely long signals. Well, a lot of our mathematical basis assumes that our signals are infinite in length, but in reality, they never are, right? So noise free, or even additive white Gaussian noise. That's we make that assumption to keep life simple, but there's lots of other noise sources that we have to deal with in the real world. We've talked a lot about lately equal probable versus non-equal probable symbols. That's actually an interesting research area to optimize the system when you don't have equal probable systems. Uniform sampling in the time domain, that type of thing. There's a whole host of other things, right? So, and in fact, when you one of the ways to actually be creative in your work and try to be innovative is to look at what assumptions you've made and try to figure out how to relax those assumptions and find out, can I do something new and unique if I don't make that assumption? Sure, it makes the math harder, makes analyzing the system harder, but a lot of times you can come up with something neat there. All right, so Let's move on. I just thought that that would be kind of fun to talk about a little bit. Yeah, my sense of what fun is a little twisted sometimes. But all right, channel characteristics. We started on this last week. So a channel needs to carry the information encoded on the signals to a distant receiver. Must also provide for the simultaneous use by many other users, right? So we need to divide up the spectrum. We translate our signals before we transmit them to a portion of the spectrum that's been allocated to us, and hopefully that portion of the spectrum is useful for what we're trying to do. Let's use cell phones for an example. Your higher frequencies, like particularly up in the millimeter wave, 30 gigahertz, 20 gigahertz, but really let's just look in 2.5 to 5 gigahertz frequency range. There's a few kind of newer spectrum allocations there. Those are great because they're the higher you go, the easier it is to access bandwidth, right? So 10 megahertz or even 100 megahertz is kind of small relative at 5 gigahertz, but 10 megahertz down at 20 megahertz is huge, right? So by going to higher frequencies, you get much more bandwidth. So we know from Shannon's capacity theorem we can get more data through. So if you're wanting to watch video, high def video with fast frame rates, or you're doing some gaming, and so you have similar type of information, yeah, high frequencies are great. Problem is they don't penetrate concrete with rebar, reinforced with rebar very well, right? So to try to get those signals from an exterior base station tower inside an office complex or a shopping center or something, that's really hard. So down at VHF, maybe 700 megahertz range, you get much better penetration through building walls and that type of thing. So in the old days, before we had so much spectrum, I think Verizon was one of the carriers that kind of locked up a lot of that 700 megahertz range spectrum, and so they were known to have good reception. It's a little different these days, but yeah. So different frequency ranges have different characteristics. But all right, so we talked about a lot of the things in the last session, but our channels have AWGN. We need to deal with multipath interference sometimes, and interference from other users. We talked a little bit about some nonlinear effects that typically happen in your power amplifier, but can happen in other places also. And Doppler frequency is a big issue in mobile communications and satellite comms and that type of thing. So, all right, up until now, we've not talked specifically about the symbol shape. We kind of kept that a little bit vague. But when we have looked at it, a lot of times we've assumed a rectangle as the spectrum. But that really hasn't been considering the bandwidth of the channel. And so reality is that all channels have some finite bounds in them. So we're going to start to look at those channels with a frequency response or an impulse response. So it's going to look like a filter. All right, so we're going to run out of time. Jump to the next Zoom session here. Okay.
That's good. See you soon.